Hello, everybody, and welcome to the Spring 2022 Fellows Colloquium. I'm going to go ahead and give everybody just a couple minutes to arrive. But while we're doing that, I just want to say hello and welcome. My name is Jenna Beckenhaupt. I'm with the Development Office in the College of Natural Sciences and Mathematics. Excited to be hosting this today. So just to let you know, this is a live session, but your camera, your mic, and your chat functions have all been disabled. If you have any issues, please feel free to go ahead and give us that email to that cnsm-fellows@csuob.edu. Also just to call your attention, we are going to have a Q&A session towards the end of this, where Dr. Balbas will be answering some questions that you may have. Feel free to put your questions in the Q&A, little Q&A box there at the bottom. Throughout the presentation, go ahead and feel free to put it in there, or you can hold till the end, whichever you're more comfortable with. And also just to let you know that this recording or this presentation is going to be recorded, so that way we can share this out with folks far and wide. So thank you again so much for joining us, and we will begin with Dean Bennett.
Great. Thank you so much, and welcome everybody to the Spring 2022 Fellows Colloquium. It's my pleasure to host the Fellows Colloquium. We do 2 a year. To be a fellow, those are the donors, the friends of the college who give us money that help make things like this possible. There's several fellows in the audience today, or fellows to be, I should say also. Margie Merrifield, who's been a great friend of the college, both as professor, member of the Chancellor's office, and then back here again. And she's been a wonderful friend of the college. Rob Friedrich and Sharon Houston are in the audience. And I want to mention them because they've made a wonderful bequest. And then, Ben Carter also. And I just want to say thank you to all the fellows. It's their donations that make the work that we do possible and really help our students get the best education they can possibly get. With no further ado, I'd like to introduce Dr. Laura Stevens, chair of our geology department, who will do the introductions. Thank you very much.
Thanks, Dean Bennett. Good evening, everyone. I am truly and absolutely thrilled to introduce Dr. Andrea Balbas tonight. Traditionally, this time period is used to extol Andrea's many accomplishments, her BS from Queens College in New York, her PhD from Oregon State. However, instead, I would actually like to tell you some of the things I think she would want you to know about her. And that is principally her passion. And I don't use that word lightly, but she has a deep passion for helping students reach their maximum potential and be able to do the things they want to do with their lives and careers. I think that Andrea wouldn't mind me telling you that she has seen firsthand some of the barriers that our students face when they're trying to become young scientists. And she has not followed what many would consider to be the typical road to a scientific and academic career. She's very, very interested in helping particularly first-generation students whose racial and ethnicities are a minority within the sciences, and those whose financial struggles are a real barrier to them completing their degrees. That deep passion has resonated with our students. We have seen that from pretty much day one when she came to the department. Despite the fact that she started in fall 2020, which was a period of extensive confusion and uncertainty due to COVID, Andrea has never lost focus of that particular mandate. She is all about the students. The students will tell you she's all about them. Our department has truly been rewarded by her presence, her commitment to students, her energy, and her scientific breadth. And tonight, I suspect we're going to get a little glimpse of all three of those. So Andrea, I hand it over to you.
Well, thank you so much. You officially made me cry, so you'll have to deal with that for the rest of your life. Okay, great job, everybody, setting this up. I'm thrilled to be here. I'm thrilled to make it to this point in my life where I can use any of the privilege I might have to help other people who have less privilege. And Dr. Laura Stevens, I just love you to death. So I'm going to share my screen. Let's see here. And I just want to say, yes, thank you all for coming. We're making it through the COVID world, and I'm so happy to be here with people who love science and the CSULB community that's pro-student. And I'm just always absolutely enthralled and enamored by all of the people trying to help these students self-actualize and ascend to a place where their contributions are valued by society the way they should be. And I'm thrilled to do this work and this life of service. I can't imagine any better life. Luckily, I get to work with Planet Earth, and Planet Earth is an amazing thing. And so it is easy for students to be very passionate about Planet Earth. So usually I start every talk the same way, and I say, hi, I'm Andrea Balbas, and there's only 3 things worth knowing about me. I like something good to eat. I like a good story, and I like good rocks because they tell the best stories. And there's just no doubt about it. You know, when space travelers go out, astronauts, they set forth into the darkness, they turn around and they look back at our planet, and they often describe it as a fragile blue marble. And I'm always captivated by that description because Earth for the last 3.5 billion years has hosted life. And for the last 500 million years, a high diversity of life. And it has continued to do that over some exceptionally bad days. So we all know the really bad day that Earth experienced with the asteroid impact that wiped out the dinosaurs. And so some of these events are so dramatic and catastrophic that they're actually beyond human imagination. And so it takes some convincing for people to actually accept the idea even that a large asteroid could hit the Earth and cause the atmosphere to be the temperature of a pizza oven, catastrophically wipe out a majority of the biosphere, all within a couple days. And luckily we have the rocks. And like I said, the rocks are the great storytellers. They're probably the best storytellers in our system, in our solar system, or perhaps our universe. And we can tease the stories out from the rocks. So Earth didn't just have one bad day. It had that bad day over here, but it had multiple bad days. And so these are the largest extinction events that we know of yet, and there are 5 of them. This large one here is often is the most catastrophic extinction event that the biosphere has experienced on Earth, and it is so extreme that it's often referred to as the Great Dying. It is hard to imagine, but that Great Dying, also known as the end Permian extinction, resulted in the extinction of 57% of biological families, 83% of genera, 81% of marine species, and 70% of terrestrial vertebrae. So for a long time, the cause of that was not known, but it's important to understand that at that time, 250 million years ago, the biosphere was quite diverse. We had brachiopods and rugose corals, gastropods and cephalopods. In the marine realm, we had the Dimetrodon that is not a dinosaur. It actually went extinct before the Permian, but it was actually lived in the shallow waters, and this big sail would help it balance its temperature. We actually had the Dinogorgon, which is a therapsid, and these are the precursors to mammals. And so these were terrestrial or continental creatures that actually lived on the planet and were actually, again, the precursors to the mammals. And these were wiped out at the Permian extinction. So is the Earth a fragile blue marble? Or is it actually a little bit tougher than that? Because remember, it's been this place that has had some sort of equilibrium to offer water for a long period of time, and conditions where life can not only exist, but diversify and evolve. So talking about tough, here are all my exquisite students. I call them my brilliant pumpkins. Look at them all. When you ask a geology student to send you a picture, they often send you a rock with their picture. As you can see here, Jojo is holding on to a rock. He is getting ready to graduate, thinking about going to graduate school in Arizona and potentially applying for jobs. Cheyenne got an RU internship at NASA this summer where she will be modeling ice. Lexi has come back to get her certificate and license for geology. The wonderful Desiree is going to Stanford this summer where she's an RU program. Annika has already finished her RU program at Columbia University and is going off to graduate school. Demetria will be measuring the oldest ice yet harvested in Antarctica this summer at Oregon State University. And then we have my graduate students. Where's my other one? Arturo here and Carl. Arturo has finished his thesis on the origin of these underwater volcanoes, and Carl is also working on the origin of underwater volcanoes. These are my brilliant students that are working on a project this semester in Barstow. Hannah won the metric scholarship and is now doing independent research. And Aaron, my thing is in the way, is going to Oregon State University to study the Cambrian explosion. So these are some wonderful students, and I can just tell you that I am absolutely enamored with them all. I think they have all the stuff to make the world a better place, and I am absolutely here to help them do that. So what we do in my lab with my wonderful students is we get the rocks to tell their wonderful stories, their amazing stories. So why are rocks good storytellers? Well, rocks are good storytellers because they record the events that they've been exposed to or the conditions that they've been exposed to. And they also have the ability to record time. In the sedimentary record, the oldest rocks are at the bottom. And then also we have fossils that we know the general age of that allow us to tell time between different layers. We have, again, relative time where the oldest rocks are at the bottom, and other cross-cutting relationships might tell us something about time. But we also have the chemistry of rocks that gives us what we call our radiometric or absolute or chemical ages. So again, if we look at a rock, we pick it up and it's rounded, we know that it has traveled and it has banged against other rocks and it has been rounded. And that's what we can see on the human scale when we pick it up and we look at it. When we look at a rock that is cooled from lava or magma, we can pick it up and we can look at it, or we can use our hand lens and we can say on this human scale, we can look at the crystals and we can understand how fast it cooled, how fast or slow that it cooled. The bigger the crystal, the slower it cooled. We can also look at the grain size and tell us about the energy of transport. There are giant boulders and there are fine clays. The giant boulders were moved by very energetic water, and the clays were laid down in a very quiet marine realm. And so while all these rocks are experiencing the conditions, another process is taking place on the atomic scale. And that process is the decay of unstable atoms to other atoms or other sets of atoms. And so this actually gives each rock kind of its own watch, if you want to picture it that way. These rocks can record when they were made, when they were moved, when they were deposited, when they were uplifted. And all of these things are related to the chemistry in the rocks, and usually having to do with a rate of decay. Here we have carbon that is decaying to nitrogen. And so when we take this atom that is the parent atom, and we know that it decays to a daughter and it has a certain half-life, we can actually use that constant decay rate to define the age of a rock. And this goes back to billions of years, and as early as hundreds or tens of years. And this allows us to put the events of Earth history into an order, a series of events. And so when we put them in those series of events, we're not just doing that so we know when something happened. We're doing that so we can test other hypotheses about the geodynamic origin of a volcano or a tectonic event. So for example, one of the things that we do in my lab, like I said, Arturo and Carl are working on dating underwater volcanoes. And here we have the volcanoes that have breached the surface, the current Hawaiian hotspot. And you'll notice that that's the youngest of the volcanoes. And as you get farther away from this mantle plume, the volcanoes get older and older and older. And as they get older, they actually subside and sink under the water surface. And so there's still a trail of volcanoes, submarine or seamounts, we call them, volcanoes, that goes all the way here to the Emperor Bend and back and up here to the north to Detroit Seamount, that is the largest, that is the oldest, and that is approximately 80 million years old. So we date these seamounts so that we can reconstruct how this oceanic plate moved. So we don't, again, just date a rock to know when it formed, but we date a rock to test a hypothesis about an Earth system, like the movement of the Pacific plate through time. Another hypothesis that we were testing was for the geodynamic origin of these volcanoes right here. And this is a blown up image of this area of the Hawaiian Ridge. Here are the modern day Hawaiian volcanoes. And these again are seamounts that are largely underwater. This Garner seamount actually has Garner Pinnacle that's above, a little bit above the surface. But these volcanoes directly north of Gardner are what we were trying to investigate. And we wanted to know how they formed. They were actually once large enough to breach the surface. And so our hypothesis was that this massive Gardner seamount had so much mass, and it is known as the largest shield volcano in the world, that it actually imposed that mass on the lithosphere, and adjacent to the pressing down, a bulge in the lithosphere or a buckle began to happen around this seamount. And we called that arch volcanism. And that arch volcanism will create fractures in the crust that will allow for melt to be formed, the decompression melt, and then ascend to make volcanoes. And how we can test that hypothesis of its geodynamic origin with geochronology is that if we know the age of Gardner Seamount, which we do, it's around 15 to 14 million years old, we can test this hypothesis by determining the age of these other seamounts. So if they are not coincident with Gardner, then they could not have been formed by the processes of arch volcanism. So how we do that is that we have to go out to sea to collect these rocks. And I get on this big ship called the Nautilus, and we use this submersible that we send down to the seafloor to collect rocks from the seafloor. And this is what it looks like when we do a nighttime deployment. And I love nighttime deployments. One time we had the submersible, its name is Hercules, coming up from the seafloor. And I saw a pelagic white-tipped shark attaching this rope. Another time during a nighttime descent, there was a large squid that started attacking the lights. So you never know what can happen during nighttime deployment. Then once it is deployed, we actually control the submersible from the ship, and this is the inside of mission control. And here in this seat, you usually have the navigator that talks to the ship and tells the ship how to move. Here you have the operator or the driver of the Hercules. Here you have the driver of the Argus, which is another submersible that actually holds the line so that the line or tether is not pulling on Hercules and Hercules can move. Here you have the cameraman. These people are usually wildlife photographers, and they're really good at zooming in on crazy and new organisms. And in the back row that you can't see, we call that the science team. And the science team will usually have a biologist and a geologist and a data logger that's logging all the data we're collecting and surveying, and a communications person that's talking about the science to the public, because these events, these expeditions are live streamed. So right now, one of my teammates, my collaborator, Val, she's on the Nautilus now, and they are currently doing dives, and she's collecting rocks for another hypothesis we have about one of the longest living plumes that we think may have lived 145 million years. And if so, if we can test that hypothesis and it is the case, that would be the longest living known plume in the Earth's history. So when the submersible gets to the seafloor, this is what it looks like. And you never really know what you're going to see. So everybody kind of gathers around in the lounge if they're not on watch to see when you reach the seafloor and get a general idea of what's going on the seafloor, even if it's their time to sleep, because the ship runs 24 hours. And once you get down there, you would be surprised. Like I said, there are biologists on the ship, a lot of them, and this is why. Even though we're going to 10,000 feet below the seafloor, there is an abundance of life. And like I said, our planet Earth is absolutely amazing in that it can supply those conditions. Now, these are deep sea corals that really weren't known very much about them until about 20, 25 years ago. And so now we're trying to identify places where they actually thrive and what are the conditions that allow them to thrive. Remember, there's no light at these depths, and so we don't know why they have colors. And they are not photosynthetic because, again, there is no light at these depths. They are completely filter feeders. And so this great diversity of life we see a lot of at 10,000 feet, especially associated with volcanic rocks that I want, because they need somewhere to hold on. So right here, I have been on many dives with many biologists. So now I know that these are cup corals, and this is a Walteria sponge. And this is a different type of coral than this coral. And these are brittle stars that are inside this coral, and we call them associates. And so we are down there to collect rocks that I'm going to date to determine the origin of the volcanoes, but we're also taking a survey of the biology. And in that survey, we often find organisms that have never been discovered before. So in the 2018 cruise that I was on, we found 7 new organisms. And here is just a beautiful image of this basalt tower covered in deep sea corals. And I just love how, so the operators of Hercules, they need a lot of practice. And so some of them are really good at this. And this is a shot where you can see that the operator or the driver, the Herc pilot, as we call them, is really good at their job. And this is about 3 different species of deep sea corals. And again, we log them, and this video is archived, and then scientists go over and count all of these organisms later. Here's a little closer to home. You see that this is a dive. I was not on this dive, but off of Santa Barbara. And we're looking at some of these rocks that are closer to California. And we have interbedded cherts here that might have been exposed subaerially at some time before they were submerged again. And we have differential erosion of whatever they are interbedded with. right? So this is Wilson Rock again. And now the Nautilus is now docked in San Pedro. So I will be doing some work and trying to get some of our students on the Nautilus so that they can experience these fantastic things of exploring the seafloor and going out to sea. When you go out to sea, you never know what you might see. So 80% of the ocean has never been mapped, explored, or even seen by humans. So I was on watch one day, I'm sitting in the back row and I see this little black dot in the distance, but I don't really like my voice on being recorded. I don't like how I sound. So I bump my scientist buddy, who is a biologist and specialist in deep sea corals, and I point. And so you'll see that that's his voice that you're going to hear right as we start this video. And so this was a video of what we saw at the end of one of our 4-hour watches. We were at the tail end. We only had 20 minutes left before we were going to get out of mission control and go down to dinner. So I'm going to show you this video of our experience seeing this organism that had never been filmed before.
Yeah, there's something dark over to the left-hand side, sort of in the center. It's moving along there. This thing here. Can you take a look at that?
What is that? Oh, wow.
Looks like a Muppet.
What are you?
What is
It's like
that?
a,
Oh, it's
it's
fish.
defensive.
It's in the water column. Isn't
That's
that
a
what it is?
fish?
What? I don't know.
What?
It
Wow.
looks like fish.
Is it engorged or is it like that?
Is it mad?
Yeah.
Touch
Is
it.
it just?
Look.
Oh
Oh
my
my
God.
God.
Look at
Oh
that.
my
Wow.
goodness.
Oh my
It's
God.
kind of like googly eyes.
I think he ate too much.
Yeah.
He's full.
Wow.
Wow.
We really ticked him off.
Uh-oh.
Wow.
Oh, what?
Are those like the gill arches? The gill?
Some kind of.
What is
Whoa.
it
Wow.
doing?
It just got so big.
It's all bladder.
Oh my God.
That's his defense, like let
Oh,
me blow
yeah.
up so I can show him how big I am.
Incredible.
Wow.
Yep, he's doing the shake.
What's a
Oh my God.
Yes.
Whoa. Is that a gulper eel then?
Wow.
Yes.
So, yeah. That is crazy.
That
That
was
That
awesome.
was awesome. What a way to end the watch, right?
Yeah, so I was the one who said it looked like a Muppet, but in my defense, I am a geologist, not a biologist. So that was the best I could do. And so during that time, so we have scientists that are logged in and they are talking to us, the two scientists that are on watch, and they're telling us to do things. So there might be a deep sea fish expert and he might be logging in from the UK and he stayed up all night to watch the dive. And there might be a cephalopod expert who stayed up and he's logging in from Japan. And they will tell you, I see something over in the right-hand side, turn Hercules to the right and go over there. I want to see what that is. And so we try to pay attention to the other scientists that we call the scientist ashore. And so at that time, when we were seeing the gulper eel, I had a scientist who was logged in from the UK who was a specialist in eels. And he was losing his mind and he was writing in all caps, "Oh my gosh, I never thought I would see this in my entire life. I can't believe this." And it was the most wonderful thing. And he was so happy that as the gulper eel was doing that, I had tears in my eyes watching this guy just frantically hitting the chat. And later he told us that that was a juvenile. And that's why it didn't swim away right away, because it was scared and it didn't know what to do. So that is the work I do on the seafloor, but I also do work in the terrestrial realm, and I study something called mega floods. So this is a great cartoon that talks about the Missoula floods. So back around 22,000 years ago, there was a massive lake, And it was caused when the glacier ice came down during the Ice Age and blocked the Clark Fork River. And when it did that, it made this lake that is about 50% the size of Lake Michigan, so a very large lake. And after the lake got big enough, it would, the dam could no longer hold the lake back, and the dam failed. And when that happened, the entire lake drains within about 3 days. And the floodwater moves across central Washington down to the Columbia River Gorge and goes out here and into the Pacific Ocean. This is a massive amount of water, and when it's released, it travels at about 65 miles an hour. It creates tectonic events, and it could be heard from, they've modeled it from hundreds of miles away. There are actually woolly mammoth bones and bodies captured in the mega flood deposits. And it scoured this whole area, and that's why it's called the Scablands. So they wanted to know some things about the timing of this event. And that is because I know it's hard to believe that this even happened once, but it happened 100 times, approximately 100 times, maybe a little over 100 times. So once this dam would fail and it would release the lake, it would scour the land and be deposited into the Pacific, and the ice dam would grow back. And then the lake would build up again, and the ice dam would fail again, and then it would cause a catastrophic flood. And over about 3,000 years, this happened at least 100 times. And so the scientists who studied this wanted to know how much this ice lobe here, that's called the Okanagan lobe, was affecting the route of the floodwater. And in order to do that, they needed to know when this flood reached over here where the ice was, and how long this ice stayed down here in its southernmost extent, where it left behind a terminal moraine. And I specialize in dating these terrestrial deposits that are known as cosmogenic nuclide surface exposure dating. So I came in and started to date these deposits and found that at around 18,000 years ago, the largest flood happened that was about 100 times the flow rate of the Amazon River. And this Okanagan lobe was at its southernmost extent about 15,500 years ago when it began to retreat. But before that, at 18,000 years, it actually wasn't low enough in the south to block all of this water. And so the water actually occupied the North Columbia River route. So I was able to tell the story about the routes of the several floods, the size of the floods, and how the floods went from larger in the beginning to smaller. And now we still have some rocks here that we can date from Ginkgo Park that I'm looking for a graduate student to work on that might tell us about an even bigger flood of that series. And the rocks I'm talking about are this big. So imagine floodwater so energetic that it can carry a boulder the size of a car. That's a big flood. So again, as the water drains out of that lake, these are all the areas that it occupies, and it's so much water trying to get out that it interacts with pinch points where the water can't flow through. And so behind those pinch points, it actually creates this lake called Ephemeral Lake Lewis that was about 400 feet deep and would be a lake that would cover a large portion of central Washington before the water could get down into the Columbia River Gorge. The water was so high that at Portland, it would breach and it would come over the sides and flow down into the Willamette Valley all the way to Eugene, where it would also create an ephemeral lake that they refer to as Lake Allison. And how they know that is because there's a rock here near McMinnville that they call the glacial erratic that came all the way from Idaho, which means it was trapped in the glacial ice, flowed all the way through Washington, through the Columbia River Gorge, out over Portland, and then this iceberg was wedged against a hill where it melted and dropped out this boulder. So these are the kinds of things that I date. I also date rocks that record the geomagnetic field, because the geomagnetic field does crazy things. It actually reverses every once in a while. Sometimes it actually weakens and the pole bounces around and it doesn't reverse. It actually bounces back to the way it was before it began. And we call that an excursion. And so these are rather dramatic events. And we know that the Earth's magnetic field has rotated many times over Earth's history. It has actually had some times where it didn't rotate. And we don't know why it does that. And so in order to elucidate some of the unknowns about the geomagnetic field, we try to understand the timing a little bit better. And so some of my work was dating the last paleomagnetic reversal to 774,000 years ago, with a weakness of the field that lasted around 30,000 years. So we know all of these large dramatic events happen on our planet. We know that crazy, crazy things happen on Earth, and the rocks record those things, and they record them very reliably. And so we also know, though, that the Earth rebounds, and it creates this habitat for this diversity of life. And so I'm often struck by, how is it and why is it that the Earth seems to uniquely rebound out of the planets in our solar system? Because we know Mars once had water and it does not have water today. And so another thing that the rocks record is that there is also constant change, not just abrupt change, not just catastrophic events, but the Earth's surface is constantly changing in the movement of the tectonic plates. And we know they change in direction and orientation and speed. And the rocks have allowed us to reconstruct all of those changes of the tectonic plates. We also know that the ice ages reliably come and go all the time. It's continuing to happen. So the surface of our planet is experiencing these ice changes, the growth and decay of ice at our poles. And again, we know that, and that it happens continually. And here is a record that's talking about the carbon dioxide associated with the changes in the global climate. And it reliably is happening every 450,000 years. So this is something that Dr. Stevens is an expert on. And these changes are controlled by the Earth's orbital relationship to the sun. We know that the sun gets farther, that we get farther away and closer to the sun over 100,000 to 400,000 year timescales. The tilt of our planet changes, and basically the rotation or the wobble of our planet changes. And that changes our relationship to the sun and how much energy we receive from the sun and how that energy is distributed through the different latitudes and longitudes of our planet. So on eccentricity, the distance from the sun happens 100 to 400,000 year timescales. Precessional, which is its orbit, is 26,000 years, and its tilt changes about every 41,000 years. And the reason we know this, again, is because of the rocks. The rocks have a certain isotopic character related to the ice and how much oxygen-16 is stored in the ice, because as oxygen-16 is preferentially evaporated, oxygen-18 is preferentially precipitated. And as you move up in latitudes away from the tropics, the precipitation becomes enriched in oxygen-16. And so the ice caps preferentially store oxygen-16. So all these little organisms that live in the water column are preferentially taking oxygen-18 during the times of ice growth. And those little organisms are made of calcium carbonate, and calcium carbonate makes up the rock limestone. Again, it's telling a story of constant change. Some of that change happens on 100-year timescales, and we know that it's being controlled by eccentricity. And then for reasons we don't completely understand, maybe the climate begins to be controlled by the tilt. And so these are things we're still deciphering, but we know that the Earth is experiencing constant change. And so it makes me wonder, and I'm sure I'm not the first person to say this, it probably is in a textbook somewhere, but is Earth's predisposition to change helping it? basically endure these more difficult days. So the amazing rock record tells us that our planet is in a state of constant change. While some changes are unpredictable and catastrophic, others are ever present and driven by the orbital forcing relationship with the sun. The constant growth and decay of continental ice caps results in a state of reliable disequilibrium. The rates of exchange between the biosphere, the hydrosphere, the atmosphere, the geosphere, and the cryosphere are not constant through time. And so could this predisposition to change be the secret to Earth's fitness to host life? Do the rocks tell us that the secret to Earth's toughness is in its state of constant change? So I wonder, is it, the constant change that the Earth is always going through, a way that it kind of resets after these larger changes? And again, this might be something, or likely something someone has already suggested or even in a textbook, but it makes me think of my students and how well they accept change, how nimble they are, how fit they are, how their hustle is so strong. When I tell them, oh, that's not going to work, you're going to need to try something else, they're right there to do it every time. And I wonder if that's just not the secret to durability and toughness. So that's all I have for you today. And I just want to thank you so much for listening and showing up. And I'm happy to take any questions.
Thank you so much, Andrea. That was so much fun.
Yay! Look, we talked about climate.
And cool videos.
Yeah.
Well, we've already got some questions lined up, and a couple of people, Holden and Elaine, are interested in the deep sea corals. That kind of captured them, and they were interested in whether or not, and you would not study this, but if you had heard from one of the biologists, whether or not it was what they were eating, or if there's a specific chemical reaction that's happening that gives them those colors that you were showing.
So we don't know, and this is a thing that we talk about at lunch and dinner and everything when we're on the ship. So there are other things that are colorful. There are squat lobsters that are bright pink. There are these other Chinoclops fish that are bright red. There's also these little shrimps that are also bright red. There are these other deep sea corals that are a beautiful lavender. And so some of the biologists have said, oh, it's just a consequence of the enzymes that they prefer to use, that there's no actual biological requirement. But so much is unknown about these deep sea communities. That's why we're there, and we're always finding something new, and we still don't know. So every time we go out, we have these long discussions and we say, where are we going to dive? Here's the seamount. Andrea needs rocks from the base of the seamount to know how old it is. And we need ones that are relatively fresh, right? So they're like, you're easy. We know what to do with you. But where are the corals going to be? And so we're always talking about, well, the current direction is likely coming from X, Y, or Z. And if the current is coming perpendicular to that ridge, would it be the best place where the corals could actually sit there and start collecting stuff from the currents, right? So even that is, we can do dives. A couple times we did 2 dives in a row, and my biologist friend was really depressed because he said he was dying catastrophically because he was expected to find life. And in those 2 dives, we didn't see any deep sea corals. So it's still really a wild, wild west out there of us trying to figure out where these corals will exist. And we don't even know why they are where they end up being.
Okay, cool. So Benjamin Carter's interested in moving a little forward in the history that you were giving. We were talking about the big extinction event, the Cretaceous event. And he was kind of curious why only the flying dinosaurs survived. Do you want to comment on that?
Do I know why that is? I have to think about that. The flying dinosaurs. I don't think I know that answer. Do you know that answer?
That's a new one on me. I didn't think any of the dinosaurs survived except for the little ones that kind of mimic what are now modern day birds. So I'm not an expert on that either.
Yeah. So I think Yes, so the smaller critters and smaller mammals lived through. So the smaller mammals are what inherited the earth. And the smaller dinosaurs that I thought actually evolved to birds were some of them, but I don't know why they did. But that is an excellent question. And because you have it, you should actually get into science and find the answer. Yeah. And that the in Permian extinction was actually the reason why I actually decided to go get my PhD. So it is a fascinating topic.
I would agree. So Gerald Williams is interested in whether or not you know of any places in Europe or Asia that had conditions that were similar to the Missoula floods.
Yes, there is the Altai floods in Russia, large floods, catastrophic floods that have around the same age range when they had a retreat of that continental ice. There is a hot debate about the Black Sea. Some people said they had floods. Some people said that they didn't have floods. Those floods are expected to be a little bit younger, around 8,000 years. But the Nautilus did dive in the Black Sea and they found drowned beaches. So this is likely gives us a lot of evidence that there was actually a catastrophic flood that drowned a shoreline. And so I hypothesized a way of testing that. Basically, I could do a burial age, a cosmogenic nuclide burial age of the sand of that beach, and be able to reconstruct when it was drowned. But we can't get back in there because it's too dangerous. Then there are other floods that happened actually to make the British Channel. All that scoured area is actually created by mega floods. So we do know now that mega floods happen not only on our planet, but on Mars as well. And if you look at the current Perseverance Mars rover, it has taken pictures of large boulders that are on actually these lake deposits, an ancient delta. And we know that those are moved by floods. And we know that the mega floods come and go with the ice ages. And it's very interesting because the first time they were proposed in 1923, the Missoula floods, this guy they poo-pooed him for so long, actually until 1957, until they finally accepted his hypothesis. And it was rocks that told the story, the reliability of the rock record that finally made people pay attention to his hypothesis of mega floods. And his name was Bretz. He had a lot, he was tough. That's the theme of our talk.
So you mentioned that these big floods on Mars. I just want to ask a follow-up question. Has any of the rovers been able to retrieve enough geochemical information to date those rocks? And if not, are you going to be the first geologist to date those rocks on Mars?
So I'm known to be the one to date those rocks. Actually, they're called erratics. And another scientist, I don't know, gave me this rock. And you see, it says Queen of the Erratics. So, but my actual postdoc advisor is the head scientist of that rover. So I'm sure he's already thinking about taking a sample of those rocks. They don't have the instrumentation on the current rover to do a cosmogenic nuclide surface exposure date, but they will, I imagine, drill a core of those rocks to do exactly that.
Excellent. Thank you. So Joseph Landeros, one of our alums, wants to know where he can watch the Hercules live streams. We all want to.
Yes, so that is happening now. They might be diving right now, and you'll see some of my buddies and my collaborator Val. All you have to do is Google Nautilus Live, and you will see. And they have 4 cameras that are constantly streaming. And so we don't always know when we're going to dive because sometimes the weather is bad, and if we have a swell, we can't put Hercules down. But you will get a general schedule of when we expect to dive, and there are 4 cameras that you'll be able to see the weather because there's a camera that points to the back of the ship. And again, I'm really hoping that Laura and I can take some students out on the Nautilus and get some good rocks and have some biologists there and see some awesome things. I mean, the borderlands, I'm sure, is just packed with life because of all the, the bathymetry, all the topography and everything. So it would be fun.
Okay, cool. So Holden's back with questions about red. I think Holden likes red. She's saying that deep sea biology tends to be red, and she heard a hypothesis that red light travels, well, it's not a hypothesis. Red light travels are shortest in water. We know that. The hypothesis is that that is why some stuff in the deep sea is red. Do you know if that's
That would make sense. So for instance, you didn't see them, but we have lasers to tell us how big something is when we're on, that Hercules has, and they're green. They're not red for exactly that reason. And I wouldn't be surprised if that is indeed the reason, because a lot of things are predating, like those little shrimp. They dance around. I can't remember. I should have brought a picture of them. They're very entertaining. But yeah, that might be it, because a lot of things down there are red. Like a lot of the things that are not corals are red.
excellent? So Natalia wants to know if you think that humanity has contributed to climate change. Oops, it disappeared on me. The question disappeared. Jenna, can you make that question come back? Is that possible? Thank you. The question is, do you think that what humanity has contributed to climate change could have a more negative impact on the way the Earth rebounds back to normal? In other words, we know it's robust, but is humanity really testing its limits, I think?
Yeah, I think so, because I mean, if we look at the records we have in the ice cores, so this is something that Demetria will be looking at this summer, we know that we have ice cores that reliably go back 800,000 years. And remember that the bubbles caught in ice cores are a direct archive of the atmosphere at that time. While they are at the high latitudes, they record the chemistry of the atmosphere. And we know that we have never seen this rate of change, of increase in carbon in the atmosphere, or anything even like this rate of change in the last 800,000 years. And we also know that in the last 800,000 years, we have never been at the parts per million that we are of carbon that's in the atmosphere today. So I think we had a speaker who came last week, my buddy Ed Brook, who is the chief scientist for the ancient Antarctic ice. And I think he said the 800,000 year record before humans started impacting it was at 280, and now we're at 450 something, right? Wasn't that something? It sounds about right. So we're definitely way above anything we had in the natural record for the last 800,000 years. Now, one of the reasons why we're going back and trying to find this old ice that Demetria will be working on is because we want to extend that record and say, hey, were we ever at a time where we had the amount of carbon that we have now in the atmosphere? And if so, what did the Earth do? How did it rebound from something like that that's so dramatic? So I do think that we're pressing the Earth into a situation that is more similar to its catastrophic, abrupt events that it's experienced in its lifetime. And so the balancing out from that condition will result in more dramatic changes of climate at various latitudes than we see in the natural rebound of the record, when it's usually just in this orbitally forced situation. So it'll be more closely related to a catastrophic event that takes the Earth hundreds of thousands, sometimes millions of years to rebound from.
Thank you. So Vic is interested in whether or not there's a connection between the catastrophic Lake Bonneville flood and the Missoula flood.
So that is a very good question. The catastrophic Bonneville flood was actually a larger volume of water, but it traveled, it actually came out of, so the Bonneville flood was actually the breach of basically an earthen dam. The flood, the lake filled to the point where it started to breach its levee, and it actually came out slower than the catastrophic breaking of the ice dam of the Missoula flood. Another difference with the Bonneville flood is the Bonneville flood happened once. The Bonneville flood was a bigger lake, and it was more in southern latitudes. It actually went through the Snake River Range and into the Columbia River Gorge. And there are actually sediments where you see multiple Missoula floods and then the Bonneville flood sediments on top of that. And the Bonneville flood, again, only happened one time related to one lake that failed. And the Missoula flood happened multiple times. The Bonneville flood, they think, happened around 17.1 thousand years ago. And the Missoula floods likely happened in between 18.2 thousand and up to maybe as recent as 13.4.
So Andrea, would it be possible for you to stop screen sharing so that you're front and center and not your slide?
Yes, how do I do this? I say, don't share no more. Don't share no more. Did I do it?
Yep, you did. Perfect. Awesome. So Joseph Gunter was interested in the benefits and limitations of the type of dating, so the cosmogenic dating that you do. What are the benefits? What are some limitations?
So that is a very good question. When you when you're doing any type of method, you need what you have is your target, which is your mineral, and the chemistry in that mineral that is your target mineral. And for cosmogenic nuclide surface exposure dating, you need to have a nuclide that is very well calibrated, meaning you have done many experiments where you compare a known age to the actual amount of the cosmogenic nuclide in a rock, so that you could know that, okay, I know that 4 atoms of beryllium-10 in 1 gram of quartz appear per year. And we call that a calibration. And so the more calibration experiments you have to better constrain the rate of production of a cosmogenic nuclide, the better that is. The one cosmogenic nuclide that we do have very well constrained is called beryllium-10, and it is made in quartz. So when I first started working on the Missoula floods, there were people who had worked on the Missoula floods for 40 or 50 years. And they told me, well, Andrea, at the southernmost extent of the Okanagan lobe, it's only basalt there. You won't find granite. So there won't be quartz there for you to date. And I said, where is this place? And they pointed it to a map. And I did like my dad said, well, how you're going to do it is wear out the soles of your shoes. And so I just started walking back and forth till I finally found 12 granitic boulders. And I had just thought, well, if they come from the Okanagan highlands, then they're going to come through an area that has granite. So that is one limitation, Jojo, for doing the cosmogenic nuclide surface exposure dating. Do you have the target minerals and the target cosmogenic nuclides? And that usually just takes a lot of work in the field. And then the next is, do you have the time range? So there are certain cosmogenic nuclides that only have a usefulness back to, say, 200,000 years. Or like radiocarbon is actually a cosmogenic nuclide, and it only has a usefulness back to around 50,000 years. And you can push it to maybe 70 if you've got really a spectacular sample and the gods are good to you. So different cosmogenic nuclides have different half-lives. Some of them are a stable end member, like neon-21 and helium-3. And so you can use those for deep time. But neon-21, for example, does not have a well-constrained production rate, where helium-3 pretty much does. So there's a lot of variables at play, and you need to know all of those variables before you approach the field, because the most important work you do in geochronology is actually understanding the geologic context of your samples. So you need to know what hypothesis you're testing with that age.
Okay, excellent. And then one final question. Jim is just really curious as to what other dating methods can be used to date a rock. And I know that you could talk for a week on this, but
yeah, so we have a lot of things we can use these days. So Dr. Alyssa Abbey will use what we call basically uranium, thorium, helium ages to talk about the uplift of and the exposure of rocks, right? I will do cosmogenic nuclides, of which some are beryllium-10 and helium-3, neon-21, aluminum-26, and that tells us about actually that is actually a relationship for how long a rock is exposed to galactic cosmic rays, which is very interesting and fantastic because they come from outer space. So that's what's producing a cosmogenic nuclide. Then you have other decay chains where you have potassium that decays to argon that tells us about the age of the origin of a rock, meaning when it crystallized. You have uranium series that can tell you about the ages of zircons. So that tells us about the oldest age of a rock that we have on our planet, which is the Jack Hill zircons from Australia that are 4.7 billion years old. You have neodymium and samarium. You have rubidium and strontium. You have radiocarbon. We could go on and on for days.
So for those of you students who are interested in this, and this is foundational to geology, being able to date things, it's not just enough to know something happened. We want to know when it happened. Dr. Balbas will be teaching her graduate seminar in geochronology in the spring of 23, if you're around. I think Elaine has one last really good question, and I think this is pertinent to the students and to possibly some alumni here, and that's what interdisciplinary research efforts do you hope to perhaps start and get going in the future?
Yeah, so that is really interesting to me. So I am an interdisciplinary scientist and what I refer to as a multidisciplinary big picture scientist. So some of the work, for instance, I want to do with you is looking at Missoula flood sediments, right? And what could they possibly record in relationship to diversity or human activity. Also, I want to look at basically, I would love to look, so there's these new hypotheses that talk about climate having a relationship to basically tectonic events. And I would like to look at how tectonic events might be related to atmospheric conditions through time. So I'm always looking at the biology when I'm on the Nautilus. So for example, even when I was on the Nautilus this last time, I stayed up even though I was supposed to be asleep because I wanted to see it reach the seafloor. And I always do that. I'm compulsed to see what's down there right before I go to sleep. I knew that I was going to have to be on my ship. So I was in the lounge and we finally hit the bottom, and I'm looking and I'm looking and I'm looking, and I see what looks like ripples, but not current ripples, wave ripples, which require an oscillatory current, right? And they're at 10,000 feet. So I'm like, where's the waves? Yo, that was my scientific question, yo. And so I said that out loud. Because I was so surprised to see them. I said, what are those ripples doing there? I said, those should only be around for oscillatory conditions of some type of movement, some type of energy. And it just so happened that the guy who discovered oscillatory deep sea waves was sitting right next to me as an oceanographer. And he said, I'll tell you what they're doing there. And he told me about the gravitational force of the Hawaiian Ridge that's pulling the ocean in during tides and releasing it. And that is actually creating oscillatory flow at the deepest parts of the ocean. And so that's just a testament to multidisciplinary work and how it can just open your mind to new hypotheses about how the world works. So I'm always open to that. And I'm hoping that if we can get these students on the Nautilus, that will be one of the primary learning experiences for them about the power of multidisciplinary science. So somebody could be doing the water chemistry, somebody could be doing the biology, the microbiology, the bigger biology. And then of course we'll be doing some rocks because you got to do the rocks. And so all of those things are intertwined. And that's where I think some of the greatest basically discoveries come from.
Well, thanks for that. At this point, I mean, you've answered a lot of questions, which is really awesome. That's the end of the formal questions. And we would like to do a little meet and greet. So I'd like to invite those of you in the audience that would like to turn on your cameras and mics so that you can chat with Andrea directly for a few moments.
Yay.